welcome back. We were discussing about the Fourier transform of rapidly decreasing function yesterday in the last video, and today in the process what you have seen is you encountered an integral over contour that is not actually from minus infinity infinity, but it is kind of minus infinity plus I into I to minus infinity plus infinity plus I. So, it is basically a line parallel to x axis at y equal to some point, okay, that is in the complex plane. It is called because it is a piecewise, it is a continuous curve, so it is a line, straight line, so it is called a smooth curve in the complex plane. So, we explained that for this function f of z, which is e power minus z square, contour the integral over that contour is actually same as integral over contour y equal to 0, that is x axis. So, we will try to show that again. I explained you briefly and used it in the Fourier transform. Today, we will try to little digression, we will just look at the how to evaluate that integral. So, just let me how to evaluate the integral. Let us say if I call minus infinity plus I. So, I try to choose the line like this. This is x axis and I choose it at x equal to 1 line. Instead of xi by 2a, I choose x equal to 1, y equal to 1. So, this is x axis is y equal to 0 and this is y axis. Okay. So, you want to do this, this what you have is this infinity plus I. So, this is the minus, so this is the contour over which you have this one, this integral e power, because this is a complex number. So, integrand this variable should be z square dz. So, I want to evaluate this integral. I will show that this is actually equal to the same as it is over here. Okay. So, how do I do this? I will try to take this, let us choose from some, let us say minus r to plus r. You make a rectangle here and you try to make a close it by this way. You close it. So, in this direction you are going. So, or if you do not want, what you do is you try to have a positive orientation. As I said, if you move along this domain inside, this rectangle should be on your left hand side. So, your thing will be like this. So, I consider this as gamma. Okay. So, let gamma be the boundary of the rectangle, boundary of the rectangle, this one. So, that is x is between minus r to r and y is between 0 to 1. So, that is your rectangle. So, r is any positive number. So, that is how you have chosen. If you choose like that, then by Cauchy theorem, that is what I explained without proof. I am not going to give you a complex function theory. Cauchy theorem tells you that if your function f of z is analytic inside some domain, you take any closed curve inside the domain, that function has to be 0, that integral value of the function over any closed contour has to be 0. So, this is and what you have is here, and if you so your domain D is actually any domain containing that whole complex plane you can think of as your domain. D is full complex plane, D is actually full complex plane. In that you have this rectangle. As r goes to infinity, every time this expands, but this is fixed. These two lengths are fixed, these two sides are fixed, and the other side, this is as r goes to infinity, this is keep going to up to it is going to be wider and wider. Okay. So, by Cauchy's theorem, what we know is over this contour, if gamma is this plus this plus this plus this, okay, this over this f of z. Now, my f of z is e power minus z square, because e power minus z square is a differentiable function, because you can just calculate e power minus z square as a u of x y. You write in this fashion, I time v of x y and you calculate this, u and v will have a partial derivatives and they are continuous functions of two variables, and then you have a partial derivatives and they satisfy those two equations that I have shown, I have given yesterday. So, these are the Cauchy-Riemann conditions that are satisfied. Okay. So, once you have this, so you can look into books, complex function theory books, so to see that e power minus z square is an analytic function. So, this is dz is equal to 0. What does it mean? Over this contour, but this contour is not you cannot represent this parameterize as a single function. So, this means this is over minus r to r, right. So, this is let us say gamma 1, gamma 2, gamma 3, gamma 4. So, gamma is a gamma 1 plus gamma 2 plus gamma 3 plus gamma 4. So, first of all I write this as a gamma 1 is over e power minus z square dz. So, what is gamma 1? Gamma 1 is, if you parameterize, this is y equal to 0, x is between minus r to r. So, you take x equal to t, y equal to 0. So, what you get is t is between minus r to r, and you have z of t is, x of t is t plus I times y of t is 0. Okay. So, this is exactly what you have. So, z of t is t. So, because of that z dash of t is 1. So, you have a dt, z dash of t dt is your dz. So, that you write it as dt, and then this is between minus r to r, and you have e power minus z becomes, z is simply z of t, that is t square. So, you have only t square. Okay. So, this is your integral, first one. So, I1 is this. Okay. So, just let me write only this one, I will not use many notations. So, similarly you can calculate what is your gamma 3 e power minus z square dz is, in the same way if you do the parameterization, this is actually y equal to 1 minus r between x is less than or equal to r. So, z of t is, x of t is x of t is t, y is 1. So, you have I 1 into I, t is between minus r to r. So, this is your parameterization for gamma 3. So, that means the parallel piece. Now, because it is going from this direction to this direction, so what you have is this is actually going from r to minus r. Okay. So, you have a minus r to minus r, and then e power minus what is your t square? T square is z square is t plus I whole square, t plus I whole square. Okay. T plus I whole square, and then dt, z dash of t is 1. So, that is dt. So, you have dt. This is actually what you want. Actually, this is nothing but, you can also see that this is also z3 is nothing but this is over minus infinity plus infinity plus I to minus infinity plus I e power minus z square dz. Both are same. So, this is exactly what you want to evaluate. Okay. So, this is what is that piece over this piece. Now, if you try to do this gamma 2 and gamma 4, what is this one? Over gamma 2 e power minus z square dz. This is gamma 2. If you look at gamma 2, that is let us say y equal to x equal to r, capital R, y is between 0 to 1. So, how do you represent this? Z of t, which is equal to r is fixed, x is fixed. So, r plus I t, t is between 0 to 1. So, your integral will be z dash of t dt is simply I times dt. So, you have I dt, t is running from 0 to 1 because you are going from this to this. Okay. So, e power minus What is your z of t? So, that is simply minus r plus I t whole square. So, what is this one? This is actually 0 to 1 e power minus r square anyway comes out e power minus r square comes out, and then what you get is e power t square, and then you have minus 2 I r t I dt, I comes out, this is dt. So, this is what is your integral over gamma 2. And similarly, you can get this gamma 4 e power minus z square dz, that is also. So, again if you look at gamma 4, x is now minus r, y is coming from because it is coming from opposite direction, should be running from 1 to 0. So, you have a z of t is r minus r plus I t. So, t is between minus 1 to 0, sorry 1 to 0. So, you have 1 to 0 e power minus r plus I t whole square, and then you have, when you do this z dash of t dt is simply I dt. So, this is also again you have a minus, so you can convert this to 0 to 1, and gamma 3 is r to minus r, right. So, not okay, r to minus r. So, that is what I have to use. So, here this is 0, 1 to 0 becomes minus 1 to 0, minus 0 to 1, and then I comes out, and then you have e power minus r square, and then you have e power I t square minus 2 I r t dt. Now, this is integrable function because it is 0 to 1, finite real part, imaginary part separately. What do I mean by this integral, finite integral a to b u of I mean z of t, that is x of t plus I times y of t dt, means a to b x of t dt plus I times a to b y of t dt. So, this you can easily see this type of thing. This is how it is defined. Okay. So, this is this. So, that is how this is integrable functions. These are integrable. This integrand is integrable function. So, now you have gamma 1, gamma 2, gamma 3, gamma 4. You all combining together, it is 0. So, what is this one? The second part. Second part is nothing but this is from minus of minus r to r e power minus t plus I whole square. Okay. So, it does not matter. So, we really do not use this one. Okay. As r goes to infinity. So, this is not really, this is not minus infinity. So, what you have is minus r to plus r, that is the meaning. Okay. So, once you combine it, because of the Cauchy theorem, what you have is as r goes to infinity, this goes to 0 as r goes to infinity. This also goes to 0 as r goes to infinity. Okay. And what is left here? This goes to what you want. As r goes to infinity, it is going to be alpha infinity plus I to minus infinity plus I e power minus z square dz, this integral. I do not look at here. Okay. But this one minus infinity infinity e power minus t square dt as r goes to infinity. So, as r goes to infinity, you can write as r goes to infinity. So, that integral over gamma e power minus z square dz, which is equal to which goes to which converges to integral over gamma 1 plus gamma 3 e power minus z square dz, because the other parts are 0, which is 0. So, this means integral over gamma 1 e power minus z square dz converges to integral over gamma 1 is minus this, what you get is x equal to 0. Gamma 1 becomes, as r goes to infinity, this converges to, let me write it properly. So, this is going to be minus minus infinity, rather plus infinity plus I to minus infinity plus I, this one plus this is going to be minus infinity to infinity e power minus t square dt equal to 0. But that is what is the Cauchy theorem. I simply have this is all 4 integrals are 0 together. As r goes to infinity, every time this gamma 2, gamma 4 which is going to 0. So, that makes it only these 2 integrals are left. So, this is exactly what you want, and this is nothing but you can reverse this limits, that makes it minus infinity infinity minus infinity plus I minus infinity plus I. This is actually, if this is the minus of this is plus this of this. So, that gives you minus infinity infinity e power minus t square dt. Now, t is minus infinity, which is the real line x axis. So, this means when you have an integral over this line is same as integral over this line, okay, but in the same direction. So, now I have taken from minus infinity plus I to infinity plus I. This is how you see this by using complex function theory. You can see such integrals you can evaluate. So, as and when when we do the applications of Fourier transform on differential equations, in other words, when you try to solve the boundary value problems, initial boundary value problems with this Fourier transform, we will see if you encounter any of these integrals, if you need to evaluate, we will try to use complex function theory to evaluate. Okay, we will use the counter integration technique, and as and when it is required, I will try to give you the information about this complex function theory that is required, so that we can move on. So, now we will just move on to explain the properties of the Fourier transform. So, this way you can before I do this properties, we can go on doing so many whatever given function, you can calculate the Fourier transform. In the process, you may encounter to evaluate, you may encounter integrals to evaluate, that you use complex function theory or otherwise calculus to do that. So, there is no end to go on doing these examples. As and when it is required, we will try to do when we do the applications. So, first now try to give you the properties of this Fourier transform that we have defined based on the intuitive proof of the Fourier integral theorem. So, after giving these properties, I will try to give you the rigorous proof for this Fourier integral theorem. So, that whatever we have defined, the Fourier transform and its inverse transforms, that are well defined, and you can believe because it is legitimate. Okay. So, let me give you the properties of Fourier transform. What are the properties which you have? So, I will try to start with this linear property, which we have done earlier. So, one is the linear property. What does it mean? If you take f1 plus constant times f2, if this is your function f, Fourier transform of this function, that means Fourier transform of this function, that becomes makes it a xi variable, which is equal to 1 by root 2 pi by definition minus infinity to infinity f1 plus f1x f1 plus c f2 of x. Okay, this whole function. So, f1x plus c into f2x, this into e power minus I xi x dx. This is what is the definition, by definition of this transform. So, this is equal to 1 by root 2 pi, you just write separately, because in this if your sum of the two functions integration is a linear property. So, you can write this separate two integrals f1x e power minus I xi x dx plus c comes out 1 by root 2 pi and f2x e power minus I xi x dx. So, what is by definition? This is f1 cap of xi and c times this definition, by definition this is f2 cap of xi. So, Fourier transformation that shows that Fourier transformation is linear. On take any two functions, sum of the functions if you apply, it is sum of for its Fourier transforms. Similarly, Fourier transform of a constant multiple of a function is a constant but same constant multiple of its Fourier transform of the function. So, that is what we see here. The second property that we see is what happens if you try to take a function. If your function is like this, Fourier transform of some scaling, you try to scale the variable with some a. Okay. So, what happens to this? This is a function of x, so it becomes xi. Okay. So, if so in other words, if you write like this, if f of x is or g of x equal to f of ax, then g cap of xi, which is equal to, so we will see what exactly and then we write it. So, by definition g cap of xi is by definition root 2 pi integral minus infinity infinity, g of x is f of ax e power minus I xi x dx, and now you simply do this integration, change the variable ax as t. So, if you change this ax as t, a dx, so our dx is equal to dt by a. So, if you do that, 1 by root 2 pi 1 by a comes out, because of dx is I am replacing with dt by a, and as x at x equal to minus infinity, t is also minus infinity. So, let us say so a is any positive number. Okay. So, let us choose a positive. If a is negative, what happens is going to be infinity to minus infinity. So, it does not matter. So, we will see exactly. Okay. So, if a is positive, this limits will not change. So, minus infinity infinity f of t e power minus I xi by xi t by a, xi by a into t. Okay. You can write this into t. So, what exactly you have is now is 1 by a times, this is the Fourier transform of f cap of, instead of xi you have xi by a. So, xi by a. So, what happens if a is negative? If a is negative, it is going to be, when you substitute the limits x equal to minus infinity, if a is negative, t is actually infinity to minus infinity. So, infinity to minus, that will give you a minus. Okay. So, what you get is minus a. If a is negative, what you get is minus 1 by a f cap of xi by a. So, that means what you get is a modulus of a if a belongs to a is positive, or rather mod of is non-zero. Okay. If a equal to 0, so there is no such function if a is 0. Okay. So, now I can remove this a positive, and what you get is, if you can see, if a is depending on a is positive, 1 by a comes out. If a is negative, it will simply come out as minus 1 by a. So, that is exactly the definition of mod a. So, mod a definition is a if x is a is positive, okay, and a minus a if a is negative. So, that makes it, when once you substitute, this is what once you substitute x equal to minus infinity, when a is negative, it is going to be infinity, infinity to minus infinity, that is minus of minus infinity to infinity integral. So, that minus comes here. So, 1 minus 1 by a, that is exactly 1 by mod a. So, this is exactly what you have. Okay. So, this is your scaling property. Now, you can go on doing like this, some more shifting properties. For example, what is the Fourier transform? If so, what you have is 1 by mod a times f cap of xi by a. So, now, if I have g of x as f of some kind of shifting in the variable x minus a can be any real number, then what happens to your g cap of xi? So, this we will see. Okay. We will see and try to write. So, we will calculate this dg of xi. d cap of xi is by definition 1 by root 2 pi minus infinity infinity f of x minus a e power minus I xi x dx. Again x minus a you take it as t, that means dx is dt, because a is a real number. When you put as a finite number, so x if you put minus infinity, it is going to be minus infinity. So no change with the limits, whatever may either a is positive or negative, the limits are as it is, and you have f of t, and what you get is e power minus I xi x is a plus t now, dx is dt. So this is exactly the what you get is e power minus I xi a comes out, and that makes it the remaining thing is Fourier transform of at xi. So what you get is here e power minus I xi a f cap of psi. If it is plus a, you will get e power plus I xi a into f cap of xi. So this is a third property. These are trivial properties that we can easily see. Okay. The next thing is, so this will also tells you the stories that if you have Fourier transform is Fourier transform of some function into exponential function of e power minus I xi r plus xi a, that is actually Fourier inverse transform of that is exactly f at the shift x minus a. Okay. So this will give you that information, shifting with respect to or other. So in a if you want to put it as another one, if g of x is f of x into e power minus I a x, then what is the g cap of xi? So for this you try to, if you calculate, this is by definition Fourier transform of g is here f x e power minus I a x e power minus I xi x dx. So this is exactly equal to, so this is simply what is this one? So you combine this, this is exactly Fourier transform of f at a plus xi. Okay. So this is f cap of a plus xi. So when you multiply with this thing, you just add its Fourier transformation a plus xi. Inverse transformation side, if you have multiplication with this, you inverse transform of this, you simply have scaling shifting with x with minus a, here shifting with plus a. So here you have to write xi plus a, more apt to write. Okay. So these are the trivial properties that we are doing. Another important thing is some modulation kind of property, that if what is the, if g of x is f x times, instead of e power I minus I a x, you simply have cos a x, then what is the g cap of xi? So modulation, why I am called modulation, because this function, this signal, you multiplied with this cosine function. So it's a kind of modulation. So you make it, put it in the oscillatory form, fx into cosine part. So what happens to this? If you actually calculate g cap of xi again, so root 2 pi minus infinity to infinity fx cos a x into e power minus I xi x dx. So cos a x I can write, what you can write, this is as sum of minus infinity infinity fx e power I a x plus e power minus I a x divided by 2 times e power minus I xi x dx. Now you split this as two integrals because based on the linear property. So what you get is 1 by root 2 pi minus infinity to infinity f(x) half times this f(x) into e power I times a minus I times xi minus a into x dx plus another half 1 by root 2 pi other integral part, and what you get here is f(x) times e power minus I xi plus a x dx. So, now this you can write it as half times f cap at xi minus a plus half times f cap at xi plus a. So, this is exactly what you get if you have a cosine part. So, f cap at xi minus a plus f cap at xi plus a, shifting with both sides, and I have to take the average. That is what is modulation part, modulation of f(x) into cosine part, if then Fourier transform is this. So, using these properties, sometimes if you have if a function is involving like this, you can directly calculate only for f Fourier transform of f, and then use this property, you can calculate the Fourier transform. Okay, so, with some corollaries of this property, similar property you can work out. I will just try to give you what if you take sine function, you have a minus here. So, minus divided by 2i. So, you have a 2i. So, minus I. So, accordingly you can just write, if it is not cosine, you can also write sine. If it is sine, what happens? So, let me write it as another property. If g of x is f(x) times sin x, then g dash of x, you can take as an exercise or look at this, instead of cosine you have sine. So, you have e power iax minus e power minus iax divided by 2i. So, instead of 2 you get 1 by 2, you get 1 by 2i, 1 by 2i is minus I by 2, because 1 by I is minus I. Okay. So, because of that this is minus I by 2, f cap of xi minus a, and now you have a minus part. So, we have a minus f cap of xi plus a. So, this is exactly what you get. G cap of xi is, this is what you get. Now, you see that this is a real part and you have this is a complex part. So, this is a complex number, right? Yeah, so that is fine. So, you have does not matter, this is your Fourier transform. You can easily see that this is your Fourier transform. But your Fourier transform. So, one question here is if you see that if f is a Fourier transform of f is a real valued function from R to R, f cap is from R to R. If f is from R to R, f cap is also from R to R. So, here if these are from real valued functions, this is a complex valued. So, g cap, g is a complex real number to real number function, g cap is complex real numbers to complex numbers. So, it is not allowed. So, let us not give this property. So, let us not so we cannot do this. Okay. So, basically finally eventually this together it is a real valued function. Okay. So, it does not matter, you can still give. So, together this is a real valued function, because once you replace this by definition f(x) into sin ax into e power minus I xi x, that all together it is a real valued function. So, g cap of xi is actually xi is a real xi. Okay, so let's do formally like this. So, you have this is one property. Some more properties are some corollaries, some properties which I simply give you. If g of x is equal to fx times cos or sine, cos ax, then Fourier cosine transform of g of x is, we will see that half times Fourier cosine transform of g of x at f of x at now this xi will be changing. So, you have a xi plus a or a plus xi plus a plus xi minus a. So, this is xi minus a plus Fourier cosine transform of f x, which is a function of xi plus a. So, this is what you get, you can verify. Similarly, for sine, Fourier sine transform also you can calculate, and you replace cosine by sine and calculate Fourier sine transform of g, okay, and Fourier cosine transform of g. So, all the combinations you can get it, and if you write this, let me write all these corollaries. If g of x is f x sin a x, then Fourier cosine transform of g of x of xi is actually equal to half times. So, what you get is Fourier cosine transform of f x of a minus xi plus f Fourier cosine transform of f x xi plus a. This is what if you get if you have a sine multiplication function. Similarly, you can get g of x is f x sin a or cos a x, then Fourier sine transform f s of g of x now of xi is actually it is basically same as what you get here. So, Fourier so you write instead of cosine transform you write sine transform phi f s of f x of xi minus a plus f s of f of x xi plus a, similar to cosine thing. Last one, another combination is f x sin a x, then Fourier sine transform of g of x of xi. This will be, we have a minus here. So, there is a small change. These things you can just work out and see. I think I made a mistake. F x, if g x is f x into sin a x, I have not done it. So, let me, so you just do this, take up as an exercise and do it. This is not Fourier cosine. So, Fourier cosine transform of f x into sin a x is, what you get is I should get as Fourier sine transforms, okay. And when you multiply f x cos x, Fourier sine transform will be both Fourier sine transform, this is okay like this, but when you multiply sin x, Fourier sine transform of g of x will be half times Fourier cosine transforms here, Fourier cosine transform of f x at xi minus a minus Fourier cosine transform of f x xi plus a. So, this is what you have to verify, okay. So, these are the things you can verify. So, if you multiplication, if you have modulation with sine function, what you get is you can see that the cosine transform of such modulus with modulation of with sine function, product of sine function with your function, this whose cosine transform will be in terms of sine transforms. Sine transform of function multiplication with the sine function is actually in terms of cosine function. If it is multiplied with cosines, cosines will be in terms of cosines, sines will be in terms of sines. That is what this properties tells you, okay. So, we will define some more properties. So, one of the important properties we have already used is f of if f is piecewise continuously differentiable function, and f dash is also absolutely integrable function. If f dash of x is piecewise piecewise smooth means continuously differentiable function. Okay, that means it is differentiable, that is also continuous. Smooth function and f dash of x is absolutely integrable. Integrable in minus infinity to infinity. That means you take any finite interval that is absolutely integrable. You have only you take any finite piece, you always have finitely many jump discontinuities for its derivative, which is also continuous. So, then what is its Fourier transform? Fourier transform of this cap, Fourier transform of this f dash is actually what you get is I xi f cap of xi. We have already seen this earlier, and we are using some when we are trying to find the Fourier transform of delta function that or generalized function. So, that time we looked at this property in the sides we have calculated. So, let us do it anyway formally. So, proof is, so you start with the definition left hand side, that is by definition 1 by root 2 pi minus infinity to infinity e f of f dash of x e power minus I xi x dx. Now, we do the integration by parts, that makes it f x e power minus I xi x 1 by root 2 pi. For this you apply these limits, minus minus plus minus, and what you get is 1 by root 2 pi minus infinity to infinity f x, and you differentiate this exponential minus I xi x, that makes it minus I xi comes out. So, it makes it plus I xi will be here e power minus I xi x dx. So, because f dash is absolutely integrable function, and f is, that implies f is also integrable function. If f is integrable, f dash is integrable, f is also integrable function, absolutely integrable function. Okay. So, we assume that so how do you see that if integral mod f dash of x dx minus infinity to infinity, if this is finite, can we say that it implies modulus of f x dx is also finite? Is this true? Can you see this one? Is this really true? So, otherwise you include in your hypothesis, and f dash both are f and f dash are absolutely integrable function. If you do, then there is nothing. So, then if f is integrable, if this means f is at infinity has to be 0. If it is not, this cannot be finite number. So, that way both these things will be 0, value at the plus infinity and minus infinity. What you are left with is I xi times remaining thing is simply Fourier transform of xi at xi. So, that is exactly what you want. This is one. So, from this, if f is a piecewise smooth function, so from this you can see that f cap of xi is actually 1 divided by I xi f dash of f dash cap of xi. Okay. So, this is what you get. So, if its f dash is piecewise smooth, once the moment you say that f is a piecewise smooth function, f dash is piecewise differentiable function, continuously differentiable. That means it is a differentiable function which is continuous. Piecewise, that we write continuously differentiable function, and these are the conditions under which you have this one. If you go on repeating like this, suppose f is a smooth function, that means you take any derivative, f n derivative is piecewise continuously differentiable function, and f dash all f n's up to f n derivatives are absolutely integrable, then that means you can repeat this process any number of times to see that f cap of xi, which you can write like 1 by I xi times f double dash of xi, this cap, okay. That means what you get is f cap, or rather you use this inequality rather than this. What you get is f double dash cap is equal to I xi times f cap of f dash of xi. Again this makes it I xi square f cap of xi. So that makes it f cap of xi is 1 by I xi whole square f double dash cap of xi. Here what you get is f cap of xi is 1 by I xi f cap of f dash of xi f dash cap of xi, Fourier transform of derivative. So you can go on doing like this. Finally, if it is a smooth function, what you end up is I xi power n f n derivatives of n. If you calculate for this Fourier transform, that is exactly what you get, okay. So this is these are one properties. You can also do the same technique for cosine and sine transforms. When the function f is differentiable, absolutely integrable over 0 to infinity, and you have certain conditions, and f is piecewise continuous function or piecewise smooth function on the interval 0 to infinity, you can apply Fourier cosine transform for the derivative, and you can calculate the just integration by parts, you end up getting some formulas for the derivative of the Fourier transform. So I will just write them, and we will see the remaining properties in the next video. So we will try. So the other corollaries. So let me write it as other properties. So if this is let us say 8th property, if f is a similar property I am writing. So if f of x is piecewise a smooth function in 0 to infinity, and integral f dx minus infinity is finite, and integral minus infinity f dash of x, this also absolutely integrable. F dash is absolutely integrable over 0 to infinity, and also f is also integrable absolutely over 0 to infinity. This is the meaning. And then what happens to f cap? So Fourier cosine transform of fx of xi is of f dash. If you calculate the derivative, 1 by what you get is root pi by 2, rather you get root 2 by pi, integral 0 to infinity f cap of x cos xi x dx. Now for this, if you do the integration by parts, root 2 by pi fx cos xi x, apply the limits, minus when you differentiate cos, you get comes out some xi comes out. So xi comes out, and that will make it plus, and you have root 2 by pi as it is a constant, and you get fx into sin xi x dx. So this is exactly, so if you, because f is absolutely integrable function f at infinity has to be 0, and this contribution is 0, and cos 0 is 1. So, you have a minus root 2 by pi f at 0 plus xi times Fourier cosine transform of f x, which is a function of xi. This is exactly the formula what you get for f dash of x, which is function of xi. Like this, we can write other formulas, try to calculate, or I leave as an exercise. Okay. Find Fourier cosine transform. So, under these conditions, the same conditions, what are the Fourier sine transform of f dash of x, which is a function of xi. Okay. And you can also go on doing for 2, and we can also do f c of f double dash of x of xi, because it is a piecewise smooth and you have that many number of derivatives. Okay. Up to you can write 0 to infinity f n derivatives of x, that function is also finite. In that case you go up to 2 derivatives. So, you can calculate this, and you can also calculate the sine transform of f 2 derivatives of x, which is function of xi, exactly you can calculate. Okay. So, find we write, so find the values, find this as taken, you can take it as an exercise. Yeah, I will give you the conclusion. We have some more important properties, for such as the way we have defined properties for Fourier transform of a periodic signal, that is the function defined over a finite interval. We have seen, we have defined what is that. If you have two such signals, you can define what is a convolution of two such functions. Here also we can do the convolution of two functions f x and g x, and its transformation as like in there you have a Fourier transform of the convolution product is a product of a Fourier transform, that is what you will see. And also other conclusion is you can derive Parseval inequality, and you can also derive Parseval's identity, that is a Fourier transform. So, square integrable of function, what is integration of square of the function, square integrable function, integration of square of absolute value of the function, what is its relation with integration of square integration of modulus of the Fourier transform. So, that is what we will see as Parseval's identity, and then we will prove this important property, that is Riemann-Lebesgue lemma. What happens to the Fourier transform as xi goes to infinity? At extreme points of xi, what happens? Like there, what you have is Fourier coefficients as n goes to infinity, they are going to 0, that is your Riemann-Lebesgue lemma there. Here we see that Fourier coefficients are nothing but Fourier transform f cap of xi, as xi goes to infinity, there n goes to infinity, here xi goes to infinity. So, here also it is going to be 0, that is what is the Riemann-Lebesgue lemma. All these properties we will see in the next video. Thank you very much.